Good afternoon. I'm Gaoyang Guan from Zhejiang University. Today, I'm going to talk about TinyLink, a holistic system for rapid development of IoT applications. Professor Dong is my supervisor. Here is my outline of my talk today. First, motivation. Recent years have witnessed significant innovations of Internet of Things. A great many IoT applications have impacted our lives. For example, smart home devices, IoT starter kits for education, wearable devices for health and exercise, and IoT devices for industrial automation. The number of IoT applications is increasing rapidly. Gartner predicts that the total number of installed IoT units will be more than 20 billion by 2020. However, traditional development approaches for IoT applications are very complex. In general, a developer needs to analyze the application first, and then consider both designs of the hardware platform and the software program. The tight decoupling of the hardware and the software, like the peripherals and the drivers, makes this problem difficult. Also, a developer needs to know all aspects of an IoT system, which raises the threshold of the development. This approach also introduces a long development cycle. There are several previous work which accelerate the development speed. In maker domain, Arduino and Raspberry Pi provides developers with the powerful processors and rich interfaces. Matrix Projects provides a platform with up to 15 built-in sensors, but the platform is fixed. It is not flexible to create customized IoT apps. IoT-Fi is the virtualization engine for building the IoT applications, but we need to generate the concrete real hardware components. .NET Gadgeteer is an integrated platform to support developing IoT applications. However, it uses the customized components, but we think it is important to develop IoT applications with commercial off-the-shelf components. Based on those considerations above, we plan to develop IoT applications in such a top-down approach. First, a developer writes his application code and sends it to the TinyLink system. And our TinyLink system takes the application code as input and automatically generates the hardware platform as well as the software program. Here, we take the smart house plant as an example. We will go through the TinyLink's development process. The developer writes the application code as shown in the figure. The code is uploaded to the TinyLink system. After getting the hardware configuration, including the software program and the hardware configuration, the developer assembled the node, and as shown on the right. Finally, he can visualize the data he uploaded to the cloud form. TinyLink target user includes the students in school, the individual developers, and the small companies which intend to build IoT applications. Let's summarize the previous example, and here is the 5 steps to create an IoT application. First, he writes the application code and uploads the code to the TinyLink server. And then the developer gets the output, including the hardware configuration and the binary program. He assembles the node, and finally burns the binary program. And next, I will show how the hardware generation system works. There are 2 challenges. First is how to select the most appropriate hardware components to satisfy the application requirements. The second is how to embrace a diverse set of commercial hardware components in a compatible manner. Here is how TinyLink extracts the user-required functionalities from the user code. Given the code, TinyLink will do text search to find TinyLink APIs, which has the prefix TL on the line. Then TinyLink collects the functionalities, including the Wi-Fi, the light, and the soil moisture. With the required functionalities, TinyLink will choose the hardware components that satisfy all the hardware components. Then, with the functionalities above, TinyLink will generate user constraints to choose the hardware components. Take the Wi-Fi functionality as an example. The constraint is total number of the components with the Wi-Fi functionality that should be greater than 1. This means that at least one component has the Wi-Fi functionality. The components will provide the Wi-Fi functionality include the main board, like Linked 1, and the shields like Wi-Fi shield, and the peripherals like UART Wi-Fi. Only considering the user constraints is not enough. We need other constraints to ensure the hardware components are in a compatible manner. First, we need to consider the hardware components can connect to each other. As shown in the figure, there are roughly two kinds of interfaces, the physical pins and the ports. At all mainboards, shields, and peripherals both provide and consume the interfaces. The provided number of the ports should be greater than the consumed ones. Moreover, we need to consider the type of an interface, as the components with different types of interfaces cannot communicate with each other. Thus, for each type of the interface, we will generate an interface constraint. Given the above constraints, we'll formulate the problem as follows. We'll find the subset of the mainboards, shields, and peripherals. Our optimization criteria is to minimize the total cost. And it will satisfy it was subject to the user constraints and hardware constraints we talked above. And in reality, there are about 210 constraints in common cases. The problem is a classic integer linear programming problem, and we utilize the LP solver to solve this problem. Now, there is a challenge to implement the software system, that is how to express the application logic in a hardware-independent manner and translate the hardware-independent code into the hardware-dependent execute code. In order to fill the gap between the user code and the drivers and the libraries, we utilize the hardware configuration to generate the hardware configuration header file, which use macros to solve this problem. And here is the software APIs. We extract 225 common used APIs from 116 projects. Currently, we implement 24 categories of these APIs. we group these APIs by their functionalities, and the most used APIs are including the LED, temperature, Wi-Fi, display, and humidity. With TinyLink API, we can cover about 89% of the total APIs we have investigated, and we left the remaining 10% unimplemented. And we can implement the projects, the 116 projects. We found that about 67% of the projects are supported by TinyLink, and we can port it to TinyLink with very little modifications. The remaining about 32% of the projects have at least one unsupported APIs, and thus cannot be easily ported to TinyLink in the current stage. And how we implement our TinyLink libraries? There are two challenges. First is each implementation requires developing efforts, and the number of the implementations may grow rapidly with the increasing number of the components. So, to minimize the implementation overhead, TinyLink heavily reuses the existing libraries. Glue code is implemented in TinyLink, serving a bundling from the APIs to existing libraries. Also, as an initial effort, we provide component templates written in C++ for developers to implement TinyLink libraries for new sensors or peripherals. We also implement a cloud-based compiler. Developers do not need to develop their own local development environment, like the toolchains. This can also minimize the space of the local client. We built the compiler on Aliyun Cloud, and currently it can support more than 20 simultaneous requests. And here is the evaluation. We implement 4 main boards, including the Arduino Uno, Linked One, Raspberry Pi, and BeagleBone Black. The number of the components in TinyLink databases are shown in the figure. We can see that using TinyLink can reduce the lines of code by 14% to 94%. The average percentage of the reduced lines of code for the 6 benchmarks is about 52%. We also evaluate the total number of solutions of each benchmark and case study, as well as their lowest costs among the solutions. And code first, here is another rapid prototyping technique, which is our target in evaluation. From the figure, we can see that TinyLink can generate many feasible solutions. And a larger searching space will provide more opportunities to generate the more feasible solutions. We also implement 3 real-world case studies. The implemented nodes are shown in the figures, including the smart Houseplant application, air quality monitoring application, and the voice-controlled LED application. While implementing these cases, we found that TinyLink can easily adopt real-world applications if the functionalities are present in TinyLink. And TinyLink can also reduce the total cost of the existing applications while achieving the same functionalities. And our TinyLink has released on our website. You can visit our website. We hope you can give some feedback and more suggestions. We also did an undergraduate in-class experiments. The class is about 2.5 hours, and there are 28 students divided into 14 groups. Here is the picture of the classes. The average number of the cases they have completed is about 7. And there are 2 groups who have completed all 11 cases. Below is the case completion time of the group 10. From this figure, we can see that TinyLink can accelerate the development speed if the developers are quite familiar with, if they get familiar with it. And we found that the group members will divide the tasks and work together in the experiments. In the future, we can do this work below. We try to do some. Now our current optimization criterion is the total cost, but we hope in the future the energy consumption and the extensibility is very important. So we want to do the multiple optimization criteria in the future, and we have been doing the better solver, which can do all the solutions for the problem. Also, we found that the IoT, we found that some IoT processing, IoT event processing, like the face recognition and the voice recognition, are very complex. We try to use the computation offloading. Especially, we want to bring TinyLink into the edge computing platforms in the future. And here is the conclusion. We present TinyLink, a holistic system for rapid development of IoT applications in a top-down approach. And now currently we have implemented 4 main boards, more than 100 peripherals. We have connected to 3 mainstream cloud platforms. There are more than 50 experimenters who have joined our tests. That's all, thank you.